Hi everyone, I'm Shanmugh Sainath, and in this presentation, I'll be sharing the work we have done as part of a term project for the subject Technology for Special Needs Education. Our topic is improving intelligibility of dysarthric speech, and this is our team, and our team name is Transformer. And coming to overview, so this is the overview of the presentation. Firstly, introduction. Dysarthria refers to a speech disorder, a set of speech disorders, uh, which are caused because of the disturbances in muscular control speech mechanism. This disturbances caused mainly due to damage in different parts of nervous system, that is central or peripheral nervous system. And these symptoms include slow voice, slurred speech, and strained voice, etc. So because of this issue, there are mainly communication problems because of which there is social difficulty like communication issues with people of our family and friends. And also, uh, because of this issue, people may feel socially isolated and depressed. And intelligibility is a measure which says how quality the speech is having for a given condition. So in general, for dysarthric speech, the intelligibility is far lower than that of the normal speech. So the normal speech is generally called as the control speech. So coming to problem statement, so we focused on improving the intelligibility of the dysarthric speech. So we try to solve this issue, or solve this issue in a machine learning approach or data-based approach, where we transfer the characteristics from the normal speech, which is control speech, to dysarthric speech. Coming to approach, we trained a GAN-based deep learning model, which takes both dysarthric and control speeches as input while training, and during inference, when we input a dysarthric speech, it will convert into normal speech or control speech. And also, we deployed the model on the web application, and whose details will be mentioned in the live demo. Coming to GAN modeling, firstly, dataset. So there are many publicly available datasets like Torgo database, USPH database. So these datasets mainly consists of two folders. One is audio samples of dysarthric voice or dysarthric speaker, and audio samples of normal voice or control speech, which is of normal speaker. And these audio samples are generally of digits, letters, common words, and few of the uncommon words, so that the data set are more generalized. And we have used the Torgo database for our project. And this Torgo database have 4 folders, and 2 for female and 2 for male. And out of 2, one is dysarthric speech, other is non-dysarthric speech. And each folder have 500 speech files or with WAV extension. So there are a total of 2,000 files. So coming to data pre-processing, our idea is to convert the speech file to an image, which will be sent to the GAN model. So to do that, we will first convert the audio file into an spectrogram using short-term Fourier transform, and we have a 33% overlap over the windows of 512 frames of the audio file. And after converting, we will again convert it into a decibel amplitude, and finally saving it as an grayscale image. So and then we will convert the grayscale image to an RGB image, so that it is compatible with the GAN model training. And again resize the image to 256 cross 256 cross 3. And again we will apply a few of the image pre-processing techniques like changing the having horizontal flip, etc. And coming to architecture, we used CycleGAN, which is a variant of image-to-image translation, where there are mainly two parts, two generators and two discriminators. So one generator converts the first domain to second domain, and there is corresponding discriminator for that. And the second generator converts the second domain to first domain, and corresponding discriminator is present. And there are 3 losses. So this generator and discriminator losses are in general present for every GAN. And this is the new law that is introduced, cycle consistency law, where we will first convert the first input image or the real image to second domain, and again we will reconvert the second domain image to first domain, and we will match this x and x cap, which is the newly generated x cap is the newly reconstructed image of x. So this is the architecture of CycleGAN. There are two discriminators, two generators, and we have two different domains. One is in this case, one is horse and one is zebra. And this is basically training flow. It combines the pre-processing step and the CycleGAN training. We'll convert the speech, Dysarthric speech and control speech to corresponding MEL spectrogram, and again we'll pass it to the CycleGAN for training. Coming to inference step, firstly, after training the model, we'll get a pre-trained weights, which is passed to this generator, and this generator is currently loaded with the pre-trained weights. Out of the generators, we only need first one where we'll convert the first domain to second domain. So first we'll convert the input audio, which is in WAV format, to MEL spectrogram, which is a JPEG image. And here involves the pre-processing, like resizing the image to 256 cross 256. And again, we'll pass it to generator. Generator will generate a control speech, which is then resized and finally converted into audio file again. So these are the parameters of training and pre-processing: sampling, hop size, FFT size, image. And we train for 50 epochs, and we are using Kaggle GPU. It is taking around 10 minutes for each epoch, and considering the maximum time that can be used, we train for 50. And we have set a batch size of 1, as we are having a RAM of only 16 GB. And these are the losses, 3 different losses that I mentioned before. And we use Adam optimizer for all the models, and same lambda learning rate scheduler. So these are the training results. Because of setting batch is equal to 1, you can see the fluctuation. If you train for more epochs, the model will be more generalized, or you can see the clear trend. And coming to deployment, so this is the website layout. In center, we can see where we can have an option to upload an audio. This wave spectral waveform can be seen in the left side. And if you click on button convert to non-Dysarthric voice, in the back end, it will do the inference step, and it will finally display the generated audio in the right side. So coming to terminal results, so you can see firstly it is converting the audio to image, and then converting the grayscale to RGB, and generating the image using the pre-trained weights, and again resizing the generated image. After resizing, we will convert it into audio, and finally we will display it on the web app. That's it. And coming to references, so there are mainly 3 references. One is for dataset, other one is for knowing more about the Dysarthric speech, and one is for CycleGAN. Thank you.